Hello, everybody. It's Mrs. Pound, and I'm back with more on Chapter 32 about electrostatics. So, our objectives today are going to be to describe the relationship between the electrical force between two charges, their charge, and the distance between them, and to compare the strengths of electrical forces and gravitational forces between charged objects. So, what we're going to be focusing on today is Coulomb's law. Coulomb's law states that for charged particles or objects that are small compared with the distance between them, the force between the charges varies directly as the product of the charges and inversely as the square of the distance between them. Now that's a mouthful, but we're going to represent that with an equation that I'm going to show you in a little bit. And the SI unit of charge is the Coulomb, which is represented by a capital C. So Coulomb's law, charge, capital C for Coulomb, the unit of charge. Before we talk about Coulomb's law, we're going to go back to the law of gravitation because they are very similar, as you're going to see. Remember, the law of gravitation was represented by a formula: force equals universal gravitational constant times the mass of the first object times the mass of the second object divided by the distance between the objects squared. So when we look at this formula, you don't have to keep copying this formula, but copy all of these things in the box in the table going down in the first column. So you should have the formula copied down in the first box. In the second box, we can see that this is the product of masses. So force is directly proportional to the product of the masses, the mass of object 1 times the mass of object 2. It is an inverse square law of distance. So the force is inversely proportional to the distance, but the distance squared. So remember, we called that an inverse square law. Remember, G is a very small number. This is 6.67 times 10 to the negative 11. That means there's a lot of zeros after the decimal point, between the decimal point and 667. So this is very small. Remember, this is a very weak force. It depends on very large masses. So we only experience gravity with large objects such as the sun, the moon, and the earth. There is a gravitational force between, say, me and my computer right now, but because we are not large masses, my computer does not stick to me. And the force is only attractive. It does not repel, it only attracts. And the final thing is, for that last box, the force of attraction between astronomical bodies, charges balanced in large masses. There is no measurable electric charge. Remember, this is huge, huge masses we're talking about. And overall, the charge is balanced. So this does not have to do with charge at all. Now let's take a look at Coulomb's law. Coulomb's law is force equals the electrical proportionality constant, represented by K, times Q1. Stands for charge. Q1 times Q2. So charge 1 times charge 2 divided by distance squared. Now notice the formula is in the same form, it's just different variables, it's just different quantities, but it's written very much like the law of gravitation. So instead of being the product of masses, this is the product of charges. So the force is directly proportional to the product of the charges. Just like gravity, the force is inversely proportional to the square of the distance. So it's an inverse square law of distance, just like gravity. So the closer the objects are, the more the force that is experienced. The farther apart they are, the less the force, just like gravity. Now, here is a big difference. The electrical proportionality constant is 9.0 times 10 to the ninth. And this is a very large magnitude. This is 9 billion, okay? This is 9 billion. So let's say we had two charges, each 1 coulomb, and of with 1 coulomb of charge, and they were 1 meter apart, that would mean that the force would be 9 billion newtons. That is huge, okay? So this is very large, but fortunately, these charges balance out, and the charges themselves tend to be very weak. So otherwise, so that's what we're going to find that uh, electrical force is actually much stronger than gravitational force. The force here is attractive and repulsive, or repulsive, I should say. Um, Charges can attract each other, they can repulse each other. So it's not just attractive like gravity. And the force of attraction between atoms combining to form molecules due to the slight unbalance of attracting and repelling forces. So, this is what holds molecules together, that brings atoms together and holds molecules together. And we know that it can take a great deal of energy to break some of these interactions apart. So, that's why I'm saying these are very strong forces compared to gravity. Okay, so if you are watching or listening to this video, go ahead, and what I want you to do is draw two circles together, one with a plus in it and the other with a minus in it, next to or at the top of your um, table next to Coulomb's law. And don't forget your 5 questions. And the objectives we covered today were to describe the relation between the electrical force between two charges, their charge, and the distance between them, and to compare the strengths of electrical forces and gravitational forces between charged objects. So don't forget those 5 questions. And I will be back with one more video about electrostatics.